All right, Wednesday, October 19th today. We actually have a day off next week from classes. 1 week from today, October 26th. It's called Advising Day. You're supposed to stay on campus. You're supposed to meet with your advisor. You're supposed to plan out your interim and spring schedules, so make sure you spend time thinking about that in the next week. I'd also be interested in knowing if, for those who might be interested, if you plan on taking differential equations in the spring. I'm going to be teaching that. We've got one section of 1110 right now, but if there needs to be a second section, it would be good to know that. So if you think you are either highly likely or might take differential equations in the spring, please send me an email. I'll send you a reminder about it. And let me know either that you plan on doing it or you might take it, just so I get a feel for what kind of class sizes we're looking at there.
Do you think it would be better to take multivariable calculus or differential equations?
Good question. Which one comes first, multivariable calculus or differential equations? It really doesn't matter too much. Some people think multivariable calculus is harder, some people think differential equations is harder. If you are familiar, if you're familiar with vectors from physics, that's a benefit as well to taking either one. I would say, generally speaking, on average, people think differential equations is a little harder. At least at first, compared to multivariable calculus. By the end of the semester, multivariable calculus might seem harder. The topics at the end of the semester for that are maybe more challenging.
Is there any way you could explain like the difference that we would still understand those?
In brief, multivariable calculus, you're focused on taking derivatives and doing integrals for higher dimensional things. It's good to have higher dimensional visualization skills. Dealing with vectors, that kind of thing. With differential equations, you've got, well, they're called differential equations, equations involving derivatives of unknown functions, and you'd like to find solutions to those equations. The concept of a differential equation and how you use it to model a certain physical system is kind of the hardest part of the course initially. Then later on we get into some higher dimensional topics in there as well. But again, with both classes, if you're familiar with vectors and parametric equations, it's helpful. We will do some differential equations in here the last month or so of the semester, and so you'll get an intro to the subject in here whether you take it in the spring or not.
Oh, they are teaching both, right?
Yeah, they're both being taught. Yep. If I offer a second section of DiffEQ, it would probably be online. And so it would be the flexibility of either taking it at 1110 or taking it online. But let me know what you plan, and again, I'll send you a reminder. Lecture A, I want to briefly also talk about mathematical jobs and actuarial jobs. We're going to start to talk about some actuarial applications of the stuff we've been doing in class. We'll continue talking more about present value and future value discrete payments and continuous payment income streams or cash flows along with geometric series. Do you think that's bright enough to see?
Yeah, it's a little too much now.
Okay.
Kind of washed out. Yeah, it's better.
And then lecture B, then we start getting into the actuarial applications. Actuarial present value is what we're going to study of a single payment. We'll review some probability, PDFs, CDFs, means and medians as we go. I'm going to give you at least 2 homework problems, maybe 3, that are not in the book. I will make up the problems for you to do, and I'll let you know the types of things as we get to that stuff. It'll be related to the actuarial present values. Just came across one of our department members, Nathan Gossett, a website with some of the highest paying college majors yesterday. So in this, by the way, this Mathematica notebook I am going to put on Moodle today, so you can look at what I've got here. I thought this was a link that I made, but I guess it's not linking. These are links. That one works. Business Insider best jobs, CareerCast best jobs. I guess this wasn't a link. Let me copy and paste it here. It's not working as a link. US News, best STEM jobs. Science, technology, engineering, and mathematics is what STEM stands for, if you didn't know. Glassdoor. I could have sworn I made these actual links. This is the one that Nathan Gossett came across yesterday or the day before. Highest paying college majors. A lot of them are engineering, but number one is computer science. Right there. A lot of them are engineering, electrical engineering, mechanical engineering, etc. Finance, you could maybe put under similar to what actuaries do. Mathematics majors. Okay, they're all mathematical, they're all quantitative. If you look under best jobs things, often you'll find actuaries as well. They are highly ranked jobs. The pay is good, it's tough. I mean, you've got to work real hard, you have to pass a lot of exams to get certified as an actuary. You have different levels of certification. But once you pass those exams, your career path is pretty well set if you like it. And you get, like I said, good pay, challenging but interesting and rewarding job. If you want to know what actuaries do, here are perhaps the 3 best websites: beanactuary.org, Society of Actuaries, and Casualty Actuaries Society. You can look these up. In a nutshell, actuaries try to manage risk. You know, there's risk in our lives. We could die tomorrow. We could get in a car crash and hopefully not die tomorrow. We could, you know, the house could burn down. These are all bad things. Insurance is meant to help you in those kinds of situations to recover your financial losses. You pay premiums to an insurance company, and they cover you if you have a loss. Maybe some of you have gotten in a car crash or something, and hopefully an insurance company was able to cover your losses at least partially. So actuaries often work for insurance companies, and they try to make estimates. They create models, probability models, to try to make estimates as far as, you know, how long will people live, how long will a washing machine last. We're going to look at washing machine problems today. How long will a washing machine last? And assess those risks and then insure against them. They also work for financial companies, investment companies, to try to help people save for retirement. These websites I would recommend going to if you're interested in the possibility of being an actuary. All right, so let's go back now and do some math. So we're going to review in lecture A today, present and future value of discrete payments and present and future value of income streams or cash flows. I'm going to come at it abstractly here, okay, but then maybe we'll do an example or two. For the discrete payments, it's going to be very helpful for us when we have level payments that are the same dollar amount, that are equally spaced in time, to know that formula that I wrote down last time for a finite geometric series. Finite geometric series. Technically, this is a chapter 9 topic. So in a sense, by writing this stuff down, we are starting chapter 9 as well. It's any sum of this form. Typically, it's common to denote the first quantity that you are adding by the letter A. It's also common to use the letter R for the common ratio. I'm using X instead, because R we're going to reserve for interest rate. That's why I'm not using R. But in each case, this is geometric because to get from the given term to the next term that you add, you have to multiply by the same thing. You have to multiply by X, this common ratio. I'll put a dot X here, meaning times X. It's not times time, it's times X. I should probably make my X's more like that. A little cursive looking. But I don't. Habits are ingrained here. Times X, times X, times X. You keep multiplying by X to figure out the next term that gets added. X, by the way, can be negative. And so when you simplify the series, you can have minus signs in here. So X can be negative. What should I call the last term? Sometimes you'll see books call it A times X to the n for the last term, and then you'd have n plus 1 terms in the series. More often, I write it as a times x to the n minus 1, so that you have n terms in the series. And we saw, what is today? Wednesday. We saw Monday that you can use a trick to figure out what this sums to find a simpler formula for this. And what it equals is this: a times, in parentheses, 1 minus x to the n divided by 1 minus x. As long as x is not 1. What do you do if x does equal 1? Actually, when x equals 1 is easier. If x equals 1, you are just really adding a to itself n times, so you get n times a. There's n terms here. There's n terms here. If I'm calling the first term a, the last term got to be a times x to the n minus 1 if I've got n terms. Okay? So this is a formula we're going to be using a lot. It would even be good to have it memorized. Okay? It makes the problems go quicker. Now, and in chapter 9. Not that you absolutely have to memorize, since you can use a note card test, but I think it's a good idea to memorize it. Now we want to apply it. How do you apply it? For those situations where we're trying to find either present values or future values of these annuities, they're called. And these annuities are level payments, the same amount, fixed intervals of time apart that we keep adding. Last time we did it with the assuming the interest rate was compounded annually. This time let's do it with a continuous interest rate. So R is going to be the continuous interest rate. By the way, you'd still typically call it a percent per year, even though it's compounded continuously. So if it were 4%, you'd still say that's 4% per year, but then you'd say compounded continuously. You're getting interest essentially all the time, at every moment of every day, even if it's only a fraction of a penny. Let's not specify a particular number. Let's say your level payments are, well, why not use A? Level payment amount equals A dollars. I think the example we did Monday was what, $100 a time, I think? Or was it $1,000? I forgot. It was either $100 or $1,000. I think it was 1,000. Once a year, starting right now. Remember that? We start at time 0, then at time 1, then at time 2. These are in years. To get the 10th payment, it was actually time 9. 9 years after the present, because we got our first payment at time 0. I'm going to draw a number line to illustrate this. And that black mark doesn't work so hot. This one here. Just got to remember to carry these markers around, ones that work well. Okay, so here's a timeline. Here's the present, time 0 right now. Time 1, time 2, time 3, etc. My first payment could be now. In fact, we will do it now, time 0. It could also be some later time, time 1 for example, or even time 2 for my first payment. But we're trying to keep things as simple as possible. Let's say my first payment of $8 is right now. My second payment of $8 is 1 year from now. My third payment of $8 is 2 years from now. My fourth is 3 years from now. If I have, say, n payments, n, since the first one is at time 0, the second one at time 1, my last one, my nth one, is going to be at time n minus 1. That's going to be my last payment. It's going to correspond to this kind of thing with that power there. What's the present value of all these payments? Here's the way I like to imagine it. I imagine, this is not literal, okay? I imagine taking any given payment and yanking it back in time. And literally imagine grabbing it and pulling it back to time 0. When you yank time amounts back in time to the present, you have to find their present value. That's what we're after, is the present value of all these payments. The total amount of all the payments is n times a. But we want to know the present value. In essence, what are all these future payments plus the one right now worth right now? That's what the present value is all about. What is it worth to you right now? If these were going to be, say you were retired, and if these were going to be payments that you received from your retirement account, what's your retirement account worth right now? That's the present value. That's what it means. So I got to yank these back in time. If I yank it back in time by 1 year, what's the present value of this payment at time 1 year from now? If I'm doing a continuous interest rate, I've got to use E. The present value is going to be A e to the negative I times 1 for 1 year. Remember, it was the amount, it was called B before. B e to the negative RT. B here is A. That's the future amount that I'm thinking of. E to the negative RT. T is 1 for this second payment. Now go to the third payment at time 2. Yank it back in time. 2 years though. Its present value is A times e to the negative R times 2. Go to the fourth value of A at time 3, yank it back in time by 3 years. Its present value is A e to the negative R times 3, etc. The last one at time n minus 1 gets yanked back in time by n minus 1 years. Its present value is A e to the negative R times n minus 1. The sum of all the present values of all the payments is the present value of the entire discrete payment scheme, this entire annuity it's called. Don't forget about the first one. I didn't have to yank that back in time. A plus A e to the negative R plus A e to the negative 2R plus A e to the negative 3R, etc. The last one is plus A e to the negative, in parentheses, n minus 1 times R. It doesn't look the same as this, but it is. What's x? What's the common ratio? Go ahead and say it loud. E to the negative R. X equals e to the negative R. So the present value of this, by the formula on the board over there, is A times 1 minus x to the n power. X is e to the negative R. That's an R there, not an n. E to the negative R to the n power. Let me write it like that initially. Over 1 minus x, 1 minus e to the negative R. This can be simplified. You can write it as A times 1 minus e to the negative R times n over 1 minus e to the negative R. You also could, if you want, maybe it's not really necessary, you could multiply the top and the bottom by e to the positive Rn. I don't know if that's really necessary. It's probably best just to leave it like that. What's a numerical example of this? Let's go ahead and pick something for R. Well, A and R. A, I'll use $1,000. R, I will use 0.04. Let me compute the present value of this, oops, not income stream, this is discrete payments. Let me put it in the other section. I could compute the present value as a summation. I goes from 0 to n minus 1, A times R to the I. You see how that works? That's a little tricky for people typically to try to figure that out. Think about this. When I is 0, that's Whoops, sorry. I want to do e. X is going to be e to the negative r. That's what I meant. And this is going to be an x here, sorry. That was confusing. When I is 0, this is a times x to the 0. X to the 0 is 1. So you get a. When I is 1, you get a times x. When I is 2, you get a times x squared. When I is 3, you get a times x cubed. When I is n minus 1, you get a times x to the n minus 1. You get exactly what I have on the board there, with x equal to e to the negative r. And I pick something specific for a and something specific for r. What's the present value? Let's guess before we enter this. I haven't specified n, so we are going to get something that depends on n, I guess. I think Mathematica will return something that depends on n. I could specify n. If you got n payments of $1,000, the total amount of all the payments is 1,000 times n. We do have to get something less than 1,000 times n, since these are present values. You know, $1,000 in the future is worth less now. It's going to be less than 1,000 times n. Ugh, that's not nice. Okay, I guess we better plug something in for n. How about n equals 20? 20 payments of $1,000. We're going to get something less than $20,000. $14,043.90. Is that the same thing you get with the formula? This was my point here. What does the formula give you? A times 1 minus x to the n over 1 minus x. Same thing. That's a lot easier to plug into your calculator than the summation is. And it's also easier to work with symbolically too. You don't have to write plus dot 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 stuff. Or summation symbols. You can just write that. One thing that might be interesting to think about, but I'm not going to think about it right now, is what happens to this quantity as r changes? What happens as the interest rate changes? You might be interested in knowing. Maybe on Friday we'll take a look at that. What about future values? I could push these amounts not, I could push them forward in time instead of pulling them back in time. To where? Well, you can push them forward in time to anywhere you want. Although if you push these forward in time to something less than n minus 1, then some of them get pulled back in time. Let's do a common thing. Let's push them all forward in time to time n. What happens when you push the last payment forward in time to time n? You just get a times e to the r, positive r power. So going forward in time, these are future values. The equation involved e to the positive r times t. Times 1 for emphasis. The second to last one, a right there at time n minus 1, that gets pushed forward in time 2 years. You get a times e to the r times 2 power. Etc. The first one way back here would get pushed forward in time by n years. The second one at time 1 gets pushed forward in time by n minus 1 years. The sum of all those is going to be the future value of this entire annuity at time n. The future value of this is going to be, this was the present value, by the way, I didn't label that. Present value at time 0. This is a future value at time n. It's going to be the sum of all these. You can write that as a, let's start with the bottom one, a e to the r plus a e to the 2r plus a e to the 3r, etc. The last one will be plus a e to the n times r. N times r. I did it in that order. I could have done it in the reverse order, actually. With these finite geometric sums, you can think about it in either order. You should get the same answer in the end when you simplify. This could have thought about it in the opposite order. This could be thought of as being the first term there. And you can think of the common ratio as being x to the negative 1 instead of x. You go backwards from right to left. Try it. You'll see you get the same thing. This can be thought of as in either order. If I think of it in this order, with this being the first term, this being the A, don't be confused by the symbolism here. That's not just an A that you see there, but in terms of being the first term of the series, it's acting like the A in this equation. Don't let the symbolism bother you. A is the first term in the geometric series. It's this entire thing here. So the A is here is playing a different role. It's A times e to the r, that is the same as the A that's over there. So being careful when we use that formula, we have the first term times 1 minus the common ratio to the n power. Well, careful. Is it n power? Yes, because you're going to, it's a little funny here. You've got n terms. Notice that's an n instead of an n minus 1. We didn't have a 0th power for e to the r at all. This is pretty tricky. X here is e to the r, and we do have n terms in the sum. Therefore, it does fit under this system here, even though you see an n minus 1 power there and an n power there. The key thing is to focus on the number of terms. So we do get e to the r to the n power because there are n terms. X is e to the r. And then we have a 1 minus x, 1 minus e to the r on the bottom. This can be simplified. You can multiply the e to the r through on the top if you like. You can write it like this. A times e to the r minus e to the nr over 1 minus e to the r. Let's go ahead and use this and see that we get the same thing either way. Back to Mathematica here. So now, A is still 1,000, R is still 0.04. X is going to be e to the positive r now. Right there. Still use n as 20. So I got 20 payments of $1,000. First one starting right now at time 0. I'm wondering what the future value is in 20 years. It should be bigger than all the nominal amounts put together. It should be bigger than $20,000. Does this summation do it? No. If I write it as a times x to the I need to start I at 1 now and go to n instead of 0 and n minus 1 if I want to match what I've got over here. Oh, wait a minute, maybe not. Sorry, that's wrong. I'm confusing myself. The A here is, I'm confusing myself here. Actually, this is right. This is confusing. The A here does match the A over here. But the first term you really want to be that A times e to the r. Maybe I should just do this. Let's just be careful here. I want the first term to be A times e to the r. Which means conceptually I should put the r first. And the x is e to the r. Now I can start I at 0 and go to n minus 1. This should be the right thing. And it is bigger than $20,000. Is it the same as the other expression? Hopefully. Actually, I can just copy and paste this one here. Yeah, that's the same. It's very tricky, okay? Even I get myself confused here. the key thing to focus on when you use this formula there is what's the first term and what's the x. And do you have n terms? And that's the power that goes there.
So is that the value of the money in 20 years or in 21 years?
20 years, because you get your first payment at time
So
0.
aren't you pushing it past n minus 1?
Right, but this would be at time 19, so this is time 20.
Oh. In the first example.
That's the nth payment at time n minus 1. So it's very confusing. You gotta really pay attention to those kind of details. Okay? You can always try to check things with the back of the book and with Mathematica and your calculator as much as possible too. All right, it's break time. After break, we're going to do quick continuous present value and future value, then we're going to talk about actuarial stuff. Let's take a 3-minute break.